Let's take a look at lesson 3-3. And what it comes down to is that if you put all of the rational and irrational numbers together, you get a set of numbers called real numbers. So if you go and turn to page 6 of your notes, we'll fill out a Venn diagram to let's explore this a little bit deeper. So what I'd like to do is place real numbers up here at the top and rational over here in this box and irrational numbers over in this box. As you start to grow as a child, though, the very first numbers that you start to learn about are basically your counting numbers, right? 1, 2, 3. So let's turn back to page 5 and look at this first milestone that everybody goes through. And again, these counting numbers, the real name of them would be natural numbers, but it starts at 1 and it's just the whole numbers that keep going up from there. So 1, 2, 3, 4, 5, 6, and it just goes and goes and goes. So pretty much any positive whole number, but one thing you need to remember is that 0 is not going to be a natural number. So let's add that to our notes. And let's just go ahead and say that it'd be no negative numbers as well. So that's our natural numbers. No fractions, no decimals, no negatives, not 0. So it's just our positive whole numbers. Then it gets a little bit confusing, you see. As you get to grow a little bit more, we start throwing more and more numbers up there to you, and we start looking at something called whole numbers. Well, whole numbers includes all of these natural numbers, and then we just threw in the 0. Okay, so we'll make a note right here for the whole numbers, not negatives. And so at this point, we've almost gotten through one of the trickier parts of this lesson. We'll look at one other set of numbers here, and it's called integers right here. Now the integers, they will take all of your natural numbers and they will take all of your whole numbers, and they will also just take all the opposites of those whole numbers, the negative whole numbers, and that creates the integer set. So let's make a little note here to see how this fits into everything. All of these sets are considered to be rational numbers. And, we'll look at the definition of rational numbers in detail in just a moment. But make sure that's down on your notes on page 5. And now we'll go back and take a look at this Venn diagram on the back. They're not a negative whole number, it's not 0, there's no fractions, there's no decimals, definitely not pi. And so 1, 3, and 5 are our natural numbers. So we're going to make a small box down here. And everything inside of this red box will be our natural numbers, and the only ones that fit is 1, 3, and 5. So let's put those in. We know natural numbers should be a rational number, and that's why it's sitting right there. Now, the next set above that would be whole numbers. So let's make a small box that's going to enclose the natural numbers there. And what you have to understand is that these natural numbers are already considered whole numbers, right? We know that, but we would call these very special natural numbers because 0 is not allowed to be a part of that. The one number that we can add on to all of these natural numbers would be 0. And this is a Venn diagram, so since the natural numbers are inside of the whole number box, all of these natural numbers are considered whole numbers. But this 0 right here, it's not a natural number. Okay? So the inside box can feed up to the outside box. Now, the next set of numbers that we looked at on page 5 was integers. So we'll put an integer box around the whole number natural boxes here. So to recap again, our integers are all of our natural numbers, our counting numbers, right? 1, 3, 5, 1, 2, 4, 216, any whole number that's positive, and 0. And then we get all of the opposites of our natural numbers. Basically, it's going to be our negative whole numbers that would be putting into this box, and then we'd be able to combine with the green and the red to say, hey, these are all integers. So looking at the top, what do we have to put in? -4, -6, -7 as examples. Now we have to start playing around with a few other ideas here. 0 and 7/10 repeating, we know that should be a rational number. So it doesn't fit in any of these. So how about we just put all decimals that are rational right here? Same thing with the 6/10. fractions, how about we just put right here, so that way we can show that they're rational. And let's make that 2/5 a negative, so that way we can show that, hey, it doesn't matter whether it's positive or negative fractions. And I'll tell you what, let's just go ahead and make the 0.6 negative. So it's -6/10. And again, just to show you, we don't care if it's positive or negative about being rational, whether it be a terminating decimal or repeating decimal or a fraction. And now we're moving on. We're down to the square root of 9. Well, the square root of 9 is a perfect square root. Now, I'd like to make a special notation here. This square root of 9 is 3, or -3, so we could at least put it in the integer box here if we wanted to, but I want to make a very special point that it's a rational number, so we're just going to write perfect square roots right here. Because anytime you see a perfect square root, it's rational, and we're going to talk about that in just a moment. And then we can come over here and we can make a notation about, hey, these imperfect square roots, the square root of 2 and square root of 5. That way we can see the difference between, how we handled the square roots. The imperfect ones are irrational, the perfect ones are rational. And then anything with pi, if pi is added, subtracted, multiplied, or divided with any other type of number, that is definitely irrational. So let's just put pi right here. And there we have it. If you put all of your rational numbers together with all of your irrational numbers, they are real numbers. The integers are just the negatives and positive whole numbers, right? The whole numbers are just 0, and then all of the positive whole numbers, and then your natural numbers are just your positive whole numbers. Now, let's go take a look at the definition of rational and irrational and compare it to this chart. If you're trying to know what a rational number is, a rational number, one way is to just determine if it can be written as a fraction. If it can be, it's rational. For irrational, if it cannot be written as a fraction, that's a big difference. So let's go take a look at our table here, okay? We can turn both of these into fractions. These are already fractions. And how do we turn all of these integers, the whole numbers and the natural numbers, into fractions? Just put a 1 under it. The square root of 9 is 3, or -3, so we can just put 1s under those, and so they can all be turned into fractions. The problem with these are that they are decimals that go on forever without a pattern, and so there's no way that we can turn those into a fraction. The same thing with pi. And if we go back to page 5 again, I have this or listed right here. So rational numbers, any decimal that stops, that terminates or repeats with a pattern. So again, it stops or it's repeating with a pattern. So we see that repeating bar on it. And that is a dead giveaway if you're looking at decimals to know if it's rational. But irrational numbers, if you wanted to look at the decimals, they do not stop. They don't terminate. They keep going forever. But they're not going to have that repeating bar on it. And that's what pi and the imperfect square roots cause. The decimals go on forever with no pattern. And so because of that, they've got their own category and we call them irrational because we can't turn them into fractions.